So some of the things we're going to talk about today is some of the products and services that you can obtain from rotaryengine.com and RX7 Specialties. We're going to do a sample build-up within this video. It's going to consist of us taking a D-Series 20B engine block, tearing it down from stock form, and going through the entire engine, building it up for a customer who ordered this engine overseas for a drag racing application. So there's two main things we want to accomplish within this video. Number one is we want to do a build-up so our viewers can see exactly what kind of quality and workmanship goes into all the engines that we build here. What better way to do it than on a cool build half-bridge 20B drag car application engine. The second thing we want to demonstrate is the breakdown of all the procedures and all the parts that go into all of our builds, and show you a video which you can now obtain with the purchase of your own engine. So anyone who wants to order an engine in the future has the availability to get pretty much exactly everything that we demonstrate within this video from start to finish. We decided it would probably be best if we don't waste time filming the actual disassembly of the dirty engine. What we're going to do is we're going to tear the engine down first, and then we're going to start focusing on all the different areas of each modification, explaining why it's important or why the customer chose the modification that he did, and take you through literally step by step, start to finish on each component. Then once we finish all the subcomponents, we're then going to go through an actual assembly stage where we're going to bolt our engine up to the engine stand, and you're going to watch us assemble the engine piece by piece until it's finished and looks something like this one beside me. So in my hand is the build sheet that we put together for the customer. Again, he's from overseas. I don't want to tell you where and who he is for confidentiality reasons. But essentially, this is a drag car application, very high boost engine, half bridge, fully balanced, clearanced, with our own apex seals and corner seals, and most of the work that you will see us do is actually performed right here in-house. Anything that we're sending out to a CNC shop to have sublet work performed, we'll tell you about as we go. So let's go through some of the highlights on this build. We are starting off with a D-Series block. It's one of the strongest blocks that Mazda ever made, and it's a designation for the series of 20B engine that we're using. We are going to be obviously tearing it down and completely cleaning and glass beating all the components that we perform those processes to. We're going to be decarbonizing the rotors and cleaning up all the grooves in the rotors and measuring things and making sure everything is acceptable. The modifications that we recommended to the customer to support his Bridgeport drag race motor are as follows. We're going to replace all the bearings with coated race bearings. We're going to do all of our in-house oil modifications within the gears themselves and also matchboarding the gears to the block. We are going to enlarge all the oil passages and perform the rest of the oil modifications that we normally do within the oil pump land area. And in this particular case, it gets a little bit more intensive because we're actually going to be blocking off the oil traveling through the upper dowel pin area, which is normally the passage that feeds all the stationary gears on a 3-rotor engine. And we're actually going to block those off and externally feed all the gears and bearings externally from a oil source controlled by a number 10 pressure regulator. Now we are going to have to send out some of the engine components for a machine shop to do some of their work that we just can't accomplish when we're with our in-house mill and our own drilling equipment and porting tools. It is necessary for us to have some of the stuff done on a CNC where we have actual programs. And in the case of this 20B, we actually have asked the machine shop to do things sort of on a one-off basis. We're going to do the external oil feed a little differently than we normally do, and we'll probably end up explaining that later. Some of the other stuff we're going to do here on camera is we're going to polish the 3-rotor eccentric shaft in-house with our polisher. We're going to do all the porting and polishing here, including the half Bridgeport work. We are going to do the clearancing on the rotors, both side clearancing and tip clearancing. We are going to show you the work that we have done at the CNC shop on the rotors, which is the lightening of the rotors, and also the combustion chamber modifications, and last, the clearancing around the combustion chambers. At that stage, we should probably have all of our components ready to assemble as sub-assemblies, and then move on to the actual assembly on the engine stand. A couple other things that we're probably going to be demonstrating on the video is actually balancing each rotor on its own axis on our balancer, and then doing the entire rotating assembly where all the bob weights are fastened to the E-shaft, and we spin it up and do the counterweight corrections. That's kind of a really cool thing to watch, so look forward to it. So some of the last things you're going to see after we're finished all the port work is we're actually going to lap the side housings right here in-house and show you us mounting up the plates on the lapping machine and showing the before and after finish. Further to that, it's going to be mounting the center housing to the Mazda factory engine stand and building up the motor. So here we go. So this is just a demonstration, essentially, of some engines that were freshly removed from the motor itself. Everything's just in need of a lot of cleanup. We're going to show you the difference between how they look now and how they're going to look later. If you focus down on the rotors as well, these are all the factory seals in the rotors, which we're going to remove, and then we're going to put these through a refurbishing / cleanup process. And we're going to update you once we get to that stage where all the parts are clean and move forward from there. Okay, so just as samples, these are the 3 pieces that we showed you earlier before cleanup. This is just one of the 3 rotors. As you can see, all the seals have been removed. This has been soaked in a chemical and completely stripped of all carbon and dirt and grease. It's got the original bearing in it, but it's a decent usable rotor, and we've measured this and measured all the apex clearances, and this rotor has been proved good to go. Side housing, essentially you can see it's cleaned up front, back, inside and out. Essentially this one here is ready to send out to machine shop and have some of our oil passages done. And once it comes back, we're going to be moving on to doing the porting on the intake port, and then the half bridge, and then finally lapping the face. Rotor housing, again, cleaned inside and out, pretty much ready for use with the exception of it has this really restrictive 20B sleeve. We're going to take this out and we're going to put in a 3rd generation turbo sleeve, and then we're going to finish the port work on the inside here, and by the time we're done with that rotor housing, it will be ready for install. So the next time you see it, we'll pretty much be ready to go. So now what we're going to do is mark the rotor housing for porting. We're just going to put on the little jacket on the outside with the dowel pin through, and then we're going to take the template and we're going to line it up, and we're just going to take our porting marking compound and we're just going to spray that like that, and what we end up with is something like this. It doesn't look like a lot, but by the time you pull out the really restrictive sleeve and you actually remove all this material and then build the beveled edge and chamfer it and polish it, it actually is a lot of material that we're going to take out. So now for the nasty part of the job, we're going to do the intake ports and the exhaust ports over here. Essentially we got this little station that's got lots of light, an actual light inside the rotor housing. We've got lots of die grinder bits and polishing grinders here, so we can save time and not have to change bits all the time. That's why we have so many die grinders and so many different bits. And all we're going to do here is put on some goggles, and we are going to work at, before we do the actual port inside the rotor housing, we're actually going to remove this restrictive sleeve. Okay, so what we're going to do is we're going to cut through this side and knock the roll pins through and get rid of this ugly nasty sleeve. Okay, here we go. So we just got the sleeve out. As you can see, we've got grind marks here and here. We punch the roll pin through on each side. The sleeve just falls out. Now we're going to put in our FD type sleeve. We're going to secure it with new roll pins, and then we're going to start working on porting the actual exhaust port, matching it to the FD sleeve and doing a little bit more transitioning and polishing. So now that we're done with the exhaust marking, we're going to mark the intake ports. My personal preference when we're doing a secondary half bridge is this Extreme Rotaries template. It's a beautiful piece. This is not the largest bridge template you'll ever see, but that's one of the reasons we've chosen it. We actually aren't going for a large aspirated type bridge. We're doing a very small half turbo bridge. And all we're going to do is just mark it the same way we did the exhaust, and pull out the dowel pins, pull off the template, and that's what we have to work with here. So this is all going to come out. We're going to transition, smooth that, polish it, and we're going right through there. So the bridge marking is going to become a hole, and you're left with a bridge for the corner seal to ride on. Hence the reason it's called a Bridgeport. So we'll be able to show you the complete final product when we're all done. So now that we finished doing the intake ports on the center housing, what we're going to do is we're going to choose the right drive for the lapping machine. So we have a adapter for the rear housing, we have one for the front, we have one for the thick 20B iron, and then we have, actually this is the thick 20B iron, and this is the one we're going to use for the center. So we're just going to lock this in, and then I'm going to walk this over the machine and put it on the table. And then I'm going to lock it down in the right position. Close the door, plug it in. You never want to have it plugged in when your hands are in there. And we're going to push the hydraulic arbor down, and we're going to turn it on. And that's going to sit there and lap for about 4 to 6 minutes. So last we took you to our porting area, where we showed you grinding away at the various different housings, doing different things for our half bridge port. Part of that was taking out the restrictive 20B sleeve and putting in the 93 up RX-7 turbo sleeve, and we have done so on all 3 houses, and we've finished performing all of our final port work on these housings as well. So each of them looks like this by the time they're done. These are actually painted and ready for install. So these are going to stay right on the bench here until we're ready to put the engine together. Moving over to the end housings, again, we did all of our porting and polishing in the runners. We did all of our porting and polishing at the port itself. Essentially, what we end up with is we have a much larger primary port, which has been ported and polished equally on all 3 primary ports, and all the secondary ports have been polished and secondary bridge port added up here, which is going to be consistent between this side of the thick housing and then the front port and the rear housing port, which all have the secondary bridge. You'll also see that these housings have all been lapped to perfection. These surfaces, along with these finished ports and along with the oil modifications that we've had done at the machine shop, are actually now ready to fit the bearings and ready for install. So what we've done now is we've sent out the block to the machine shop to have all of our internal galleries enlarged and a lot of our special pieces built so we can block off the existing oil system and work on externally feeding the gears. And what we're going to show you first is an example of what we're doing in-house on the gears. So this is a gear that came out of the motor like this. Dirty, factory bearing, good shape by the looks of it, but we're going to show you now what our gear looks like when we've done all the cleanup. We've checked this one out, inspected it properly, and it is good for use. We've gone ahead and cleaned this up, obviously. We've enlarged the gallery and match ported this to the feed from the block, and now we're going to push in a brand new bearing. So the final stage we're doing with these gears is just pressing the bearings into the gears, and then we're going to insert the new lock screw with Loctite in this hole to lock the bearing in place, and these gears will be finished and ready to install. So just installing the lock screw. Got some Loctite blue on these lock screws, and once we run these down, we are finished with these gears. We've already done the center bearing, and if you look here, what we end up with is 3 gears with new bearings that all have the enlarged and match ported oil feeds. So the last thing we're going to utilize the balancer and the V-blocks for is to actually spin the crankshaft with the drive motor so I can polish the crankshaft with the crankshaft polisher. It's a long and boring process, so we're not going to film the whole thing, but just so you know, our belt's attached to the crank. The crank will spin with the electric motor once we hit the start button on our keypad, and essentially what we're going to do is we're going to hold our polisher to the journal on the weight of the machine on top of the belt, and it's essentially going to polish each journal one by one. We're going to go through that process and show you the crankshaft when it's all finished. Something else we've done for the oil modifications, just to go with our new bearings, is we've actually had all the journals on this crankshaft polished. So that's what we've done. We haven't taken off any material other than minimal, talking tenths of a thousandths of an inch, just to polish up the crank and make all the journals perfect. So we're going to clearance this rotor to a proprietary specification. I can't tell you what that is, but we're going to remove the same amount of material from both sides of this rotor. We're going to start with the non-gear face so we can square it off, and then flip it over and do the non-gear side last. Okay, so here we go. Not sure if you can hear it cutting from where you are right now, but it's a tool called a face mill. It's got 4 very sharp blades on it, and this allows the finish to be extremely fine and accurate. Probably won't be able to see the material being removed from where the camera is sitting right now, but when we're all done this cut, we'll show you what the final product looks like when we're done. And we've got about another half a minute here. Thank you. Now it's done. So just pop this off for you. Have a look and see. So there's the non-milled side, and that is our new clearanced and milled face. On the rotors, we have actually already gone to the extent, as we showed you earlier, they were cleaned up, measured and inspected. This rotor here has actually already had our in-house side clearancing and our additional tip clearancing done on all the tips, and we've actually pressed in a calico coated bearing on the inside, which is a deep groove Mazda factory race bearing. All these oil mods we're doing provide extra oil flow to the engine and the reliability for a race engine. It's pretty important stuff. So we have received our rotors back from the machine shop that has finished performing the clearancing on the combustion pocket here. We've done that on all 3 faces, on all 3 rotors. We've also showed you earlier that we finished doing our face clearancing and our tip clearancing, and of course installed the new Mazda race bearings. And what we're going to do next is we're going to balance each of these rotors on their own axis and then we're going to move to a dynamic balance of the rotating assembly and doing our counterweight corrections. Okay, so now we have one of our freshly and finally machined and worked on rotors that's ready for final balancing. And we've got it spinning right now. We expect to have to do at least 2 corrections on it, which means we're going to have to remove this rotor from the balancing equipment, bring it over to the mill table, use our slot drill and do some corrections, and probably go back and forth a couple of times. Sometimes that can take as many as 5 or 6 times, but let's see how far out this rotor is, and then we'll know once it stops spinning. So it's sampling at just under 800 RPM and measuring, taking its last samples to about 786 RPM, and it's sampling one last time. This one must be out, which is normal. When you do clearancing and the combustion chamber modifications, it is very likely that the rotor is going to be far out from the factory Mazda balance. And hopefully we'll know in a minute here what this one shows and reveals itself to be. Yeah, okay, so we're not too bad. Right now we're 4.3 out on the right and 0 on the left. So we're going to have to do corrections on one side of this rotor only. While we're gone, we're going to do up the other rotor and see if we can't get them both back to 0. And then we'll do the rotating assembly balance. See you soon. Okay, so what we're doing here is we're just locking down the rotor to the mill table now that we know what corrections we need to make to the rotor after we just spun on the balancer. So we're going to line up the first tip of the rotor with the slot drill, and once we get this all lined up properly, we're going to do some correction work. We're probably going to go somewhere in the neighborhood of 30 to 40 thou deep on this one, just based on experience on doing these rotors. And lock the table, and here we go. Okay, that is our first correction. We're going to have to flip this over and do the other side, but just so you can see, the amount of material we took off is quite minimal. It's a 3/4 inch slot drill, or 19 millimeter, and that's about 5 grams worth of weight. So now we got to turn it over and do the other side. So we just finished doing our last correction with the slot drill, and took out the appropriate weight that the machine told us to remove from this rotor. So now we're just going to hook up our belt drive and spin this again and see how close we got. So again, we're ramping at just under 500 RPM. Once it starts measuring, it'll start increasing the speed, and if we get lucky, we won't have to do any more corrections on this rotor. We'll already be at 0. Now we're speeding up. We're up to about 600 RPM, 725, 780, and it's topped out about there, 798, 842, 836, and it's measuring. There's now sampling, counting down. Let's have a look and see where it ends up here. So it's still asking us to take out 4.9 on the right, so we're going to have to do one more correction after this one. Okay, there we go, our last spin, and we're 0 on both sides, so this rotor is now finished and ready. So we're going to get the counterweights ready to put on the eccentric shaft on the balancer. As you can see, this counterweight is a little rusty from being located externally on the engine. Sometimes these engines, when they're shipped from Japan, they have no transmissions attached. So we just want to protect the sealing surface on the hub side of the counterweight, and then we're going to take this over to the glass beater and make it look like new. turn this on. Within about 60 seconds, we'll have this thing looking like brand new. Okay, so all done glass beating that counterweight. Sort of as a before and after. That's the final product here. And then what we're going to do is we're just going to take some Scotch Brite and we're going to clean up the sealing surface on the hub of this counterweight and make it shiny and like brand new. And that's what you get. That's our final product. It's going to go get rinsed under hot water and then blown dry. Front counterweight, just a little bit oily. Like to put everything in the engine as clean as possible. So we're going to bring both these over to the sink and we're going to spray them off with brake clean, and then we're going to bolt them onto the crankshaft. See you soon. So what we're doing now is we're going to work on balancing the engine. We've got our bob weights here that we had custom made many years ago. Probably one of the most accurate methods of balancing today. So we're just going to finish putting on the weights on the bob weights and make sure that we've got exactly the weight that we calculated. Bingo. So we're just going to slip on the last of the 3 bob weights onto the customer eccentric shaft and lock it down, and we will be ready to go to the balancer. Already. Okay, so now we have our counterweights and our bob weights on the E-shaft. We've got everything as an assembly mounted to the machine. What we have to do now is just connect our drive belt to the motor. And we have to hook up our magnetic RPM gauge here. Just going to give it a quick spin to make sure it's centered. And last thing we need to do is we need to just put a little bit of lubrication on the journals. Okay. And then we're going to come over to our keyboard and prompt the start button. There we go. Now this machine is designed to take some measurements as it's spinning. So it's going through what's called a ramping phase right now. And as soon as the machine is comfortable, there's no major problems with the balance of the assembly, it will actually start to increase the RPM. So if you look here, the RPM is actually at 435 right now. As soon as this ramping message turns to a measuring message, the RPM will substantially increase, and then the balancer will start taking its measurements and recording. Sometimes it can take a minute to a minute and a half for that process to happen. Now it's starting to sample measurements, and you'll see the RPM is almost doubled. And if you look at the actual rotating assembly, it's spinning much faster than it was before. Once we start doing our corrections on the weights and adding or removing material, you'll find that from the time that you hit the start button up until the time where it actually samples and then measures and shuts the machine off like it just did, the time frame will be much less. In this particular case, the front is actually already corrected to 0 and the back is asking us to remove 9 grams. So we've got this one actually pretty close so far. So the nice part about this machine is we actually have a sliding mill table that runs parallel to the balancer, that when we swing this around 180 degrees, we are actually lined up dead center to the middle of the crankshaft. which is a real nice feature. And what you'll notice too is that this particular balancer has a air locking mechanism. We plug in the air line. We actually have control with a button to steady and position the mill head so we can get it to stay where we want. So we're going to go ahead and set this up, and then we'll bring you back to when we're going to do the correction on the actual counterweight. So we've got our mill head and our drill bit lined up where we've marked the rear counterweight, and the goal here is to take out 9 grams. So I always put a magnet over top of where I'm drilling to catch the filings, and just going to make sure this is perfectly center. That's right on the money right there. So corrections actually happen right on the balancer, right on the V-blocks. We don't actually have to remove these weights because of the benefit and the luxury of having this mill head lining up right on the path of where we're drilling. So we're going to do our corrections, and then we're going to spin it again. So working forward with the oil modifications we've done, first thing we're going to do is we're going to put some Vaseline on the O-rings for the rear pedestal. Now this is a pedestal that we got from Extreme Rotaries that we've actually gone and blocked off one of the factory passages. And the reason we've done that is because we're not using an internal pressure regulator here at the base of the block. That gallery is actually going to remain open. This is going to be all externally fed and regulated by a Peterson number 10 regulator from the outside. So all we're doing is we're basically using this passage here to feed the rear stationary gear, and that is all. So only the rear stationary gear is getting fed from this block. We will also be using this block on the other side to externally feed the center housing, which we've done, again, an external modification on here, and we're going to be feeding it through a number 8 fitting, and this will just simply thread in here like this. We will no longer have oil flowing through the upper dowel pins, and the way we're going to stop that is we've actually gone and O-ring groove these pins, a very, very shallow groove. So we're going to lubricate this O-ring, and we're actually going to press it into the rotor housing, and same with this one in the back, and we're actually going to be able to block oil flow going through the pins with a slug. So the oil can't go through and it cannot go around. And that's how we're going to seal off the oil from going this way so it doesn't end up leaking out here. And there's really no reason to have internal oil flow anymore when you've got control over feeding the gears from the outside like this and like this. Lastly, we're going to be coming out of the oil pump land, out of this gallery, through this number 8 fitting, and we'll be going back in through this number 8 fitting for the front gear. And sorry, speaking of the oil pump land, what I was talking about here, this oil pump land area has actually been ported and bored out here to give us the highest flow possible. So when the oil is discharged this direction, out to the rest of the oil system, we are no longer going to be flowing out the front cover. We've actually got a T-top plug fitting here, which is going to plug off that gallery, and this plug is going to plug off the feed to the original oil metering pump drive gear. So essentially all this is sealed off, and all this machine work that we had the machine shop do is specifically to keep all the oil fed externally and not retain any of the internal oil feed functions that Mazda designed the engine around. So part of the prepping, what we're going to do is we've got a special Viton rear stationary gear O-ring. We have factory tension bolt washers, including the brand new large washers for the large tension bolts. And we have some special Viton dowel pin O-rings for the top of the rotor housings. And all we're going to do, like we do with all of our O-rings for these engines, we just take a little bit of Vaseline and apply to the O-rings, just enough so they can sit in the housings and they'll stay. Now we'll always double check, obviously, to make sure that they're in place when we're going to assemble the next piece, but Vaseline serves as a great product to actually just retain the O-rings in place. And we will do the same thing with the rear stationary gear, and we'll use Vaseline also on the rear tension bolt washers, so that way when we torque them and the washer has a thin bead of Vaseline, when the washer sits on the rear plate and you torque the bolt, the rubber doesn't get jammed up and start to break. So it's a good idea to lubricate these washers. It's also very important that you lubricate the tips of the threads with oil so you can get an accurate torque reading. So we've got our Viton stationary O-ring on, and put a little oil on the gear before we slipped it in. We've got the gear mounted, and now we're just going to use our torque wrench and torque all the bolts. And once we finish torquing all the bolts on all 3 gears, we're going to pretty much start the assembly process. So stand by, here comes the fun part. So I've also just finished fitting some custom Viton oil control ring O-rings on all of the new oil seals. We're putting in new springs, all new parts in the rotors essentially, and of course we're installing our own rotaryengine.com treated 2mm apex seals. Very, very high quality, high boost seal, one of the best on the market. So now we got all our rotors all packed with seals. What we're doing now is we're just lubricating the bearings and the gears to make sure that we've got enough lubrication for dry cranking when the engine's ready to fire. And as soon as we finish this, we're going to start assembling the block over here. As you can see, we have the middle plate bolted to the engine stand, gear side up, and that's essentially assembling just like a 2-rotor engine, pretending that this is the front plate, and that's where we're going to start. All the rest of our pieces are laid out. Mike's going to pass them to me one at a time, and we're going to go through this very quickly. And one of the reasons you want to do that is to make sure that your silicone that we apply at the bottom of the dog legs of the housings doesn't dry by the time you're done torquing. So here we go. So, lubrication, center rotor, crankshaft please, Mike. Okay, now we're going to do something that's really important, which is we're going to square off the corner seals to the grooves. So when we push the apex seals down, we make sure there's not going to be any binding and we're not going to get stuck. Otherwise we've got to take everything apart again. So if you do this, you'll have the least amount of problems. Sealer. Where's the sealer? Another thing too is everywhere you have to apply sealer, you're better off taking a rag with some carb clean or some brake clean on it first and wiping off any oil that may have soaked into the cast iron that's going to prevent the sealer to stick. So we've already done that. We've already cleaned off all the areas. And that goes for the rotor housings too. So make sure that those are nice and clean on both sides. And I'm going to start with rotor housing number 1, the center housing. Okay. I'm going to lubricate the apex grooves so when the seals and the springs go down, they travel down nice. I usually start with the top one. In other words, wherever the apex is pointing straight up and down. Grab a clean rag, Mike, put some brake clean on it so we can just clean up this lubrication. Solid corner seals make it a little bit trickier sometimes to get everything in place because you don't have the mobility of the spring movement and the seal movement that can move around inside of the rubber insert in the standard Mazda corner seals. Anyone who's assembled an engine before will understand exactly what I'm talking about, but sometimes this can go a little smoother. And setting a time record isn't the goal here. Obviously making sure everything goes together accurately and properly. But again, just a little trickier sometimes with solid corners. We've chosen to use the solid corners on this build because this is a very, very high horsepower, high boost application that's going into a drag car. And anyone who knows anything about tuning and rotary engines knows that bad timing will assassinate factory corner seals and break one or several or all of them all in one shot. So we're just making sure that that's not going to be the case. If your tune is really, really good and an experienced tuner has tuned the car and you're pretty confident you're not going to have fuel system failure or something catastrophic happen to the engine, you can get away with factory corners on extremely high horsepower, high boost applications. But in this case, again, we've got a little bit of protection built in. Okay. Sometimes this one's tricky on these street rotors. All the way around, and make sure our O-rings are not falling off. Slowly down. There we go. There's our intermediate housing installed. So we're a third of the way there. So what I'm going to do, I'm going to rotate this so our lobe is at 6 o'clock. Makes it a little bit easier to set everything down in the proper alignment. So our back rotor. Okay, same thing, square off the corner seals. So again, solid corner seals can be a little tricky sometimes to be in perfect alignment with the rotor slot. And that's why it's real important to set your rotor down almost exactly where you know it's going to be. One of the reasons I clock the tip of the rotor to either the 6 o'clock or 12 o'clock location, I can pretty much promise that by the time I slide my back plate on and I get my gear alignment, that the rotor is not going to want to twist or turn. And at this particular moment, we have perfect alignment on all of our seals, so we're going to put the next rotor housing in place. Here we go. Make sure we're clean. O-rings in place. Now, we have to make sure we use one of our special dowels with the O-ring groove on it, and the O-ring to seal off this passageway from the rear housing. So we're just going to Vaseline this a little bit. Make sure we get good penetration into the rotor housing. Perfect. So we'll start again, 6 o'clock, apex tip. That one's down. It's down. Oh. The other problem too, with not so much solid corners, but in general, whenever you buy an aftermarket 2-piece apex seal, even our own rotaryengine.com seals, the corner piece, you have to glue them on. And sometimes the super glue allows the pieces not to stick, or it lines up a little tiny bit crooked, and when you go to slide it in, it wants to pop off. So those two are going to get re-glued back on again. It'll take a matter of seconds to do that, so we're going to finish up the back rotor, and we'll put those ones in the front. There. Clean off all this oil that is on the edge of the rotor housing. Make sure everything's perfectly clean. Put our dowel O-rings in place. Now we're just going to silicone the back housing, and we're going to drop it on, and the back half of the motor is done. And it's really important too to put the silicone to seal the bottom dog legs of the housings as you need to. Don't do it in advance, because if you get hung up on stuff like these tips from the apex seals, or something's not cooperating and you need to buy more time, you don't want to develop a layer of skin on the silicone and have the silicone start to cure. So that's the whole reason we always silicone last. So we just cut for a second so we can get those two ends glued back on the apex seals. Another thing I wanted to tell people is, even though these ones did not break off and they're still attached with glue, I recommend putting a blob of silicone on the tips, of Vaseline on the tips of the rotors right above that end piece of the apex seal. Just on the off chance, when you set a housing on, if something gets bumped or knocked, and it wants to load up the apex seal and it wants to pop that corner off, rather than the corner popping off here in my hand in close proximity where I can retrieve it, when you go to set the housing down, and if one of these lets go, at least you have a little blob of Vaseline as a barrier to prevent the loaded corner piece from springing up under spring pressure and flipping out. And then you got to search for it on the ground. So some people, I heard, assemble the small corner piece of the apex seal. Mike's going to watch, by the way, when I lower this down, just to make sure that everything stays in place and that the O-ring of the back plate is still in its proper location. Once they're seated down and you've got the weight of the housing on it, you're pretty much good. You don't have to pay attention to anything else. But some people decide or choose to set the corner piece down without gluing it on after they slide in the long beam. I personally don't like that idea. It's too the chances of something popping back out is greater, and this way we can just make sure that everything stays in place. Once you torque the motor, just like a Mazda factory 2-piece seal that's glued together from the factory, you put some torque pressure on it, and as things start to sandwich closed, as you're rotating the motor over, which we do anyway, when we torque, we rotate the engine around, and you'll find that you'll hear the end pieces popping loose. I'm not trying to educate anyone on that. That's pretty standard experience for anybody. But the point is the end pieces will break off. Okay, so anyways, apex seals are not going to snap loose until we get some good torque. What we're going to do right now is just put some preliminary load on the 13B length 10x1 bolts from the back. These are the only ones that hold the back half together alone, and you just need enough pressure to sandwich the assembly. One thing that's real important too, that I always tell everyone to check, especially on the 20B, is once you've got some preliminary load and you know that the housings are starting to touch each other. In other words, you've overcome the O-rings and compressed everything together. you should have somewhat of a line bore. So when I push up on the bottom of this crankshaft, it should pop up and it should drop back down under its own weight. Let's try. No problem. See the way that moves up and down? That means we're in the right direction. So now Mike's going to rotate the engine stand so we can go the other direction and do the front half of the motor. There she be. So we've already got some Vaseline on these O-rings. They're ready to drop right in. Obviously make sure your puzzle joint's in the cold area, right around the intake port. And which is right there. The outer O-ring in, doesn't matter how this one goes in. Okay, so we have our keyway in place for the second lobe of the crankshaft. That's what's going in next. So real simple, slide it down, line it up, and put some pressure on it until it seats. That is seated, that's all it takes. So one of the things we did when we just went to brake real quick is we put the flywheel nut on and we actually rotated the crankshaft from the bottom to make sure our lobe again was either at 6 or 12. We chose 12 o'clock in this case. And again, this will just make it easier for us to clock the rotor where we want it, so we know it's going to line up with the gear when we put the plate on. And now we're just going to straighten out corner seals again. Put silicone on. Oop. Back rotor housing. Make sure the O-rings are in. They are. Now, same thing on the front. By the way, 20Bs have dowel pins that are deliberately cut back and have some extra slop to allow some movement in the front section of the engine. So when you torque it down and rotate the engine, these dowel pins with the play will actually allow the front section of the motor to move and correct the line bore on the front journal. So that taper has to go down, and this O-ring in this case has to go towards the oil feed or towards the gallery. And something that's very, very important if you want to make sure your line bore is correctable and locates itself properly. A lot of guys I hear say, oh, we just use regular 13B dowels and have no problems. Well, I got news for you. You got lucky, and you're getting lucky every time. And I bet you'd have less crankshaft wear and bearing wear if you had maintained the adjustment in the line bore. Be it as it may, I choose to do it this way. That's the way Mazda designed it, and that's the way we're going to keep it. And we haven't had problems by using that method. Now that's when you're not using any studs or extra dowels either. When you start putting in extra pins and extra studs into a 20B, that's when things get real complicated. And we've got a solution for that too. There's two solutions that you can use. One of them is you have to implement that exact same movement and cutback on your additional dowels, so you don't lock up the motor and align everything rigid. So we have a way to build that into our dowel pin motors, and the way to do it when you're doing a studded motor is to put a little extra clearance on just the front housings. So rotor housing, front plate, where the one-piece studs go all the way through from the front of the motor to the back. The race studs that have a nut on either end. Those are the ones that you absolutely want to have interference fit on the back, just like a regular stud kit would be on a 13B, and extra clearance on the front, and you'll maintain that factory line bore adjustment function of the engine. Okay, we are ready for our last piece. Oh, by the way, I was going to tell you, the second way to, and this is actually the most accurate way to do it, if you want to fully stud and dowel an engine, and you haven't got the program, a CNC program, or the equipment, or the know-how to add that adjustment into your pins and your measurements and your plates, we can actually sell you a RotaryEngine.com Speedy Sleeve, which are designed to go over the rear and the front gears. And what you're doing is you're using the center factory XY axis of the middle plate bearing as your guide. So you deem that as 0. And then you put a 30 thou Speedy Sleeve that we make over the footprint of the front and the rear gear. And you actually have to correct the line bore by boring out the factory stationary gear footprint. Okay, front plate's on. That being said, what I was talking about the Speedy Sleeves is, although it's a simple function of putting a sleeve over a gear, 6 1/2 dozen the other, it becomes necessary to use some kind of CNC equipment to rebore the footprint to align the front and the back plate to the center XY axis. They both take a lot of work. That's why guys want to come places like RotaryEngine.com to get their work done. We use 2 RX-8 gears. They're nice and tall. They work as good spacers, and an RX-8 hub as just a mock-up spacing, so we can install the front nut, and we can allow Mike to be able to spin the engine from the top or the bottom. So we're going to put a little torque on that. What you'll notice is now we're able to rotate the entire assembly from the top, and if we switch over to the flywheel nut, we can crank it from the bottom. And that becomes important when you're torquing the engine, because now what we're doing is we're putting bolts from the front, bolts from the back, and we're going through a torque sequence, which is, it's important. It's not easy to memorize, and it's something you sort of have to do by feel as well, especially when you do a studded motor, because the studs will put heavy loads in certain positions. I will tell you one thing a lot of people don't know. There are some extra large tension bolts. These ones here, we're putting actually brand new ones of the long ones in. And then you have these extra large front ones. A lot of people are like, what are those for? Well, I'll tell you what they're for. The whole business of setting the line bore on the engine requires rotating the engine as you torque it down to allow this front section to float and move and allow the front of the crankshaft and the bearing to position this plate. The large tension bolts are designed to actually use to pull the engine together while you're correcting and setting the line bore. Because once you torque up all the bolts, this section can't move anymore. So you want to gradually torque these 2 from the front and the large 2 from the back, gradually as you're spinning, and this plate will find itself. This whole front section, rotor housing plate and dowels with the cutbacks, okay? So just like the back section of the motor, all we're gonna do is put some preliminary torque on the front bolts so the front half of the engine stays together. We don't have any long through bolts holding the engine together yet, so we're relying on the 13B bolts in the back, and we're relying on these short bolts in the front just to hold the motor assembly together until we can at the very least get our large tension bolts in the engine. And those have to go all the way through from the back or from the bottom. What I choose to do in this position, or at least where we are right now, is get Mike to spin the engine over. In other words, rotate the crank handle on the engine stand and turn the engine 180 degrees so we can start putting the long bolts in from the top. So go ahead and spin it over. It's pretty, isn't it?
It is. Very pretty.
So there we go. So these guys here, that's that one and this one. All right. Now there is a extra long one, just like on the 13B, that goes here. I have a tendency to like to put the outside bolt that has the protective coating on the ribs, which is, where did it go? I saw it earlier. Okay, my eyes are failing me. Where is it? This one. Mike's got it. And the rest can go wherever they want, wherever you put them. Okay? Okay, so what Mike's going to do is he's going to rotate the engine using the flywheel nut while I put some preliminary torque on the large bolts. We have a little bit of tension on the small 10 mil bolts, which are essentially going to be torqued later, but we do have a little bit of pressure on them at the moment. And now we're going to put some on the front as he keeps on spinning this engine around. And we're talking, you know, less than a couple of foot-pounds. Literally just bringing this gradually together. And he's just going to keep on going until we probably get in the neighborhood of 10 to 15 foot-pounds on these bolts. Okay, and he's going to continue spinning. Well, we put a little bit of preload now on some of the bolts from the front. So we're going to do the 3 o'clock and the 9 o'clock position first. Front and back. Now we're going to go a little below 3. Sorry, a little below 9. And a little above, and the one right below 3 o'clock on the back. And that's all we're going to touch for the 10 mil bolts right now. And once we're done with those, we're actually going to go back to our large bolts. And what I found is that the large bolts are still relatively snug and haven't loosened off too much from applying pressure to the other ones because they're in a strategic location there. They're in a good spot to keep the torque even and across. So now what we're going to do is we're actually going to put some preload on the bolts that are diagonally across from the large bolts. So opposite pattern, these two, or these four I should say. So we got 10 o'clock and 11 o'clock, and we got 4 o'clock and 5 o'clock. Same thing, we go down here, put a little torque towards the top. Just where those other bolts are, there's actually only one down there that corresponds to these ones. And now we're going to put a little torque on the remainder. And notice Mike does not stop rotating that engine. Very important. And then there's a bunch of guys out there going, oh, we do it all the time. We use an impact gun. We just suck it together and it works good every time. Good luck for you guys. Congratulations. Better safe than sorry, right? Okay. So now we've got preliminary torque on just about every tension bolt on the entire engine, including the ones with the dog legs at the bottom. Okay. So, one more time. Thick bolts. Quarter turn. Okay. Okay. Mike's done. He doesn't have to turn anymore. Now what we're going to do, we're going to start a torque sequence. We're going to start with 22 pounds on our big bolts. There we are, 22 pounds. We're almost there. It's almost clicking right away. That one. We're there. Okay, now we're going to do this. Now it gets to be much like a 13B. You start going up, down, left, right, and one clock position at a time. These ones here are always a lot looser. Not a huge deal. If they get tight and last, we always want to put some torque on them to keep it relatively even. Now we're going to bump this up to 28. 28. Large bolts again. Okay, engine's all torqued. We're just going to rotate the engine around a few times. Make sure we don't feel any sticky spots or resistance. So far so good. We did hear a couple of the end pieces break off on the apex seals. Depending on where they were glued on, some of them may not break until the engine first fires or cranks over to decent speed, like starter cranking speed. Anyway, not to worry, they'll come off, trust me. Crankshaft. If you lift up in the back, falls down, that's probably about as good of an indication of the line bore being bang on as you're going to get. So we're going to flip the engine over and we're going to spin it from the front. So we still have this mock-up spacer system here. Everything feels good. Same thing. Pick up the crankshaft, falls on its own weight. Line bore is as good as it's going to get. I'll just say from here, we finish everything behind the front cover. Put the front cover on, torque this front bolt properly, put the rear counterweight on, torqued the back flywheel nut properly. And this engine is ready for taping up and putting into a box and going to its destination overseas, which I cannot tell you where it's going, but hopefully we'll read about it soon. So since we showed the assembly video, I went ahead and finished up the front end of the motor and put the front cover on. Basically taped up the engine, banded it to a skid, and sent it to our customer overseas. You'll have the engine in 2 days. We hope everyone enjoyed watching that video, and we want to say that there's plenty more of that where it came from, but we wanted to get your opinion first on whether or not you viewers are interested in seeing more. So here's a little sneak preview as to one of the next projects we want to undergo, and we're actually going to put this on video as well. Would be really nice to hear back from people to see whether or not you guys want to see this. It's going to take a lot of time and effort. This is a personal engine of mine, which I'm putting in my 3rd generation RX-7 to replace the regular ported motor that's in it right now with an all aluminum 20B, which I designed over the last few years. My personal engine, which I have been designing for the past few years, which is going to be an all aluminum 3-rotor turbo engine for my 3rd generation RX-7. What I've done is designed a lot of this engine around the rare and very well designed and built racing 13G crankshaft that Mazda built back in the 80s for 3-rotor racing. So the unique thing about this 13G Mazda factory race crankshaft is not only they lightened it with several more holes for lightening, but this crankshaft is actually stronger than a factory 20B crank. And one of the reasons they accomplished it, or one of the ways they accomplished it, is all the main bearings and rotor bearings are actually 1 millimeter oversized. And if you look at a standard main bearing from a 3rd gen and see the puzzle joint there, not only will that bearing not slide onto this journal, but the one that will, the 13G main bearing, is actually tubular and seamless. There's no seam at all. These are competition race bearings, no different than the rotor bearing. If you look at the main rotor bearing, again, it's got a puzzle joint, and if we try to fit that bearing over top of the 13G crank, it will not fit. The seamless rotor bearing, 1 millimeter bigger with a deep groove, of course, mates the journal perfectly. The other nice thing about this 13G assembly is they actually made custom 13G gears. Bored out larger to accommodate the 1 millimeter oversized bearing. These are actually billet gears. These are not cast. These are machined from billet. And they are very hard and very strong. And as you notice too, we've got double the holes for mounting in our aluminum block on both the back and the front gear. Now we also have these are brand new by the way, we also have a brand new 13G center gear, same thing, larger bore, bigger bearing, much harder, and we've actually built one of our 30 thou speedy sleeves for this to go over top so we can actually correct our line bore. So we're going to show a little bit of how we go about fitting this gear, why it's important, the whole crankshaft rotating assembly with the custom 3,750 gram rotor weight balancing built into the crank. We're going to be correcting that a little bit. If you notice, the factory counterweight is a big heavy 20B counterweight. Here's the one for a 13G, much lighter, and it's also billet steel. Same with the rear, billet steel. And the taper for the back of the crankshaft is also 1 millimeter larger. So these have to go with that 13G crank. Again, there's a comparison from a 20B counterweight and the 13G race counterweight. The other important thing that we're going to talk about in the video is the fact that when you use a larger oversized bearing, you actually have to bore the rotor out larger to accept this. So this is one of my 8.5-to-1 rotors that we've done our CNC work on the combustion pocket, which brings it down to about 8.3 compression. We've done the clearancing on the combustion chambers, we've done the side lightening, the side clearancing, and then we're going to rebalance these on their own axis. If you notice, this factory bearing will fall right through here. The bore is too big now. The larger bearing will be pressed in no different than we press in any other bearing. So we're going to get into that in great depth and detail in the video and show you how all this is done and give you all the reasons why it's done. So again, this 3-rotor engine is fully aluminum. All the rotor housings and all the end housings are aluminum, and this is RotaryEngine.com's own 2-piece thick center housing, which we designed and had manufactured for us. This has all the internal cooling system and oil drain back work built in. This is not a drag race aluminum housing like the Turbo Smart housing, which just has a bunch of through holes for cooling. This is internally cooled with all the proper oil passages. All these aluminum housings are coated with a Cermet coating, which we have applied, ground, and then they come back here and we lap them ourselves on our machine. So this exact 2-piece center and all of these aluminum end housings, which we've done all the work on for the stud kit and the tension bolts and all the oil passage to externally feed the oil, is stuff that we've had done, but we designed and did ourselves with the cooperation of a machine shop. Even the work on the block, if you see my rotor housings, have all been machined to accept not only dowel pins in the combustion area, but race through studs that have a nut on either side that go all the way through the block. There's a couple more studs we haven't put in the block, but if you see, the engine is loaded up with extra studs and extra dowel pins. And of course we had these rotor housings stripped of the original chrome and Cermet coated inside as well. So this coating in here is all a custom Cermet coating. We're going to be running 3mm 2-piece Iannetti ceramic seals in this engine, and we're going to aim for probably somewhere around 20 pounds of boost. This is going to be a long and winding project, and although we're halfway done with most of the machine work that we needed to do, there's still a lot of sublets and machine work and a lot of balancing and a lot of fitting of bearings, a lot of oil modifications, and of course the assembly work that we have to do. So we're looking for your input to see whether or not you guys want us to follow this build and stick it up on video for you. So the main purpose of showing you guys all this stuff is we'd like to become a little bit more active on YouTube and Facebook, and give you guys a chance to voice what you want to see. So if anyone's got any requests on things that you'd like to see, I'll be more than happy to entertain them. Please just send us an email or send a message to our Facebook page. And it's been a pleasure, and I hope to hear from you guys soon.